All right, let's take a look at this problem. We have here a wad of gum falls from height h from rest straight down onto a solid sphere that's also initially at rest. If the gum hits the sphere at a height of 4r over 3, that's depicted in the diagram there, and say it sticks to the sphere, so we have a completely inelastic collision here, what is the resulting linear speed of the gum? So that's what we're being asked for. We can assume perfect rolling. What we're given is h. We're given the gum mass little m, the sphere mass big M, and the sphere has a radius r. So, all right, this is a collision. So right away that makes us think about angular momentum. And we need to then pause for a moment and ask ourselves, can we say that the change in angular momentum is zero, right? Can we say that? And in order to say that, we have to be able to um, assume that the sum of external forces on our system is going to be equal to zero. So we have to define the system. The system I'm going to define is the gum and the sphere, both of those bodies. And I'm defining it that way because, again, we use momentum analysis when we don't want to have to explicitly deal with a bunch of messy forces. So we make those forces internal to our system. And the messy forces here are the forces that occur between the gum and the sphere when you have the collision of the gum onto the sphere, which is going to be messy and complicated. That collision, your gum's weird, right? So I don't want to have to think about all those forces, and I couldn't define them well enough anyway, right? So I'm going to use conservation of momentum here. So you might ask yourself, well, yeah, okay, but there's an obvious external force on the gum because the gum is falling under the influence of gravity, right? In fact, it's accelerating. And I would answer to you, yeah, that's true. So we cannot apply conservation of momentum to the gum as it is falling from height h, as it's accelerating downward. We would not use conservation of momentum there because there is an obvious and important external force, that is the weight of the gum, which is causing it to accelerate and causing its momentum to increase, right, as it's falling downward. So we can't use conservation of momentum for the process of the gum falling. We can use it for the collision, however. So I could say at the collision, the impact point is right there at that 4/3, I'm sorry, yeah, 4/3 R. So if I just look at the instant before and the instant after the collision, I can say that the weight of the gum can be neglected right there, right? The gravitational force on the gum, I can neglect it if I look at that really short time window. I can't look at the whole time window where that force is not small enough to be neglected, obviously. But if I bring my time window in really short, I can. So what that tells me is that I need a different type of analysis for the gum as it's falling, right? So we have all kinds of choices there. You could use kinematics. I'm going to go ahead and use energy for that. So I'm going to look at here, the gum falling, and I'll use energy analysis for that. So change in energy, mechanical energy is equal to the sum of the works done by non-conservative forces. And that's just for the gum, right? We're just looking at that. And our goal here would be to get the velocity of the gum right before it contacts the sphere so that I can express the angular momentum of the gum at that point, right? Right before it contacts the sphere. All right. So what's my initial energy? This is fairly simple situation, mgh. My final is in just the kinetic value of the gum, mg. Oh, h is all the way to the ground. So actually, no, it doesn't get all the way to the bottom. So I have mg 4r over 3, because what I'm saying is that my y equals 0 is all the way at the ground there. And I obviously have kinetic energy of the gum too, 1/2 mv squared there. And my work done by non-conservative forces, we're going to neglect air friction here, 0. So this is fairly trivial to solve for V naught. If I can set my energy final and energy initial equal to one another, since my non-conservative works are equal to 0. And if I do a little algebra there, I'll solve for my velocity as quantity, 2g h minus 4r over 3 to the 1/2 power. All right, so now I have v, which is the speed of the gum right before the collision, yeah? So right at that instant before. This is what I need because I can apply conservation of angular momentum to the collision. So let's look at that. Now, this is kind of cool. I'm going to draw kind of a bigger diagram so that you can see what I need to think about here as far as geometry. And we all have kind of different geometry skills, but I'm going to hopefully inspire you to use yours here. So this is kind of just a bigger picture. Let me draw that a little bit better. A bigger picture of, I'm going to give myself a little more space here, of the sphere. And what I can say here, I'm going to just draw a few things in. The impact point, which would be like right here, right? The impact point as measured from the center of the sphere, this here is r over 3, right? Just kind of think about that. You can look at the original diagram. That's going to be r over 3. Now, I know that the initial momentum of the gum is going to be falling straight down like this, right? That's the initial linear momentum of the gum is falling straight down. And I know that r, my r value is going to look like that going from the axis of rotation, right, to that point where the force is being applied or where the impact occurs. So I care about the relationship between those two vectors. My initial angular momentum here, I can define as r crossed in with p naught, right? That's that cross product. So here you want to think about, all right, what is, when you look at these two vectors for a cross product, remember what gets filtered out in a cross product is all the parallel or anti-parallel components of those two vectors. So all you're left with are the components of the two vectors that are normal to one another. And this is sometimes talked about in math class, but sometimes not. But for me, like the physical understanding of the vector product makes everything make more sense. So this component that I'm drawing here in green, this would be the perpendicular component. And when I say perpendicular, I mean perpendicular with respect to the momentum, P naught. So that's the only component really that matters when it comes to the cross product, right? So then you might be asking yourself, how do I get at that component there? And the reason I'm doing it this way is that, yes, I could find the angle between those two, and I could just say, you know, magnitude of r, magnitude of p times the sine of the angle between them. But I mean, you'd have to do some geometry anyway to find that angle, right? So why not just find the reason that you're using the sine of that angle is in order to find the component of r that's normal to p. So why not just find the component of r that's normal to p? That's a little bit more straightforward to me. So I'm going to draw a right triangle that hopefully will kind of help you envision this. I know from teaching this a bunch of times that this can be kind of a struggle for students, but I'm going to draw a right triangle. So this is big R, the radius of the sphere. Okay, this is my perpendicular R right there. And this is R over 3. Yeah, that actually makes, that could make a right triangle. I hope that makes a little bit of sense there. So my perpendicular R is not going to be equal to the radius, obviously. That's what I'm trying to say here, right? Not going to be equal to the radius of the sphere, because this has to be a right triangle. This R perpendicular is a component of R. Yeah, so we need to find out, well, how big is that component? Well, happily, vectors, when we take their components, we care about right triangles here. So what I can say is that r perpendicular is equal to the square root of big R squared minus r over 3 squared, just using Pythagorean theorem there. Cool. All right, so that helps me. That little bit of geometry, a little bit of trig there, that helps me figure this out. So now I know that L naught, I can express this, right, is equal to r perpendicular, right? So r perpendicular is going to be square root, what we just figured out, r squared minus r over 3 squared multiplied by, now this is the linear momentum of this ball, right? So that's going to be mv. Now we just figured out v, right? We figured out v when we did the energy analysis for the gum falling, remember? So we can actually know what that looks like. So I'm actually going to go back and say, oh, right, m times 2g h minus 4r over 3. This is to the 1/2. Okay, so that's my expression for initial angular momentum. And that initial angular momentum, if I look at, I need to do my direction, right? So r cross p, that's going to be out of the page. So right-hand rule, if I cross r into p, again, direction or order matters here, right? This is not commutative. So you have to cross r into p, and that gives you an out of the page direction. Great, I could do a little bit of algebra here and clean this up. My initial momentum. That'll end up being something definitely cuter. MR, I get 16g quantity h minus 4r over 3 all over 9, and that is to the 1/2 power, again, out of the page. All right, that's just doing a little simplification. So the other piece we need here, of course, is the final momentum, and that is the angular momentum after the collision. So now the gum is stuck to the sphere, they're rolling together. So this is a little simpler to express. I have the I value of the sphere, omega final, plus the gum, which is just going to be mr squared. It's a particle, omega final. They have the same omega final, they're moving together. That's still going to be directed out of the page. This is a solid sphere, so the I value for a solid sphere is simply 2/5 mr squared. You can find that on the table. So final angular momentum is going to be 2/5 mr squared omega final plus little m big R squared omega final out of the page. So you can clean that up a little bit there too. And now since we've made our argument that we can use conservation of angular momentum because we're looking at just the moment right before and right after the collision. So then we can set my initial angular momentum equal to final angular momentum, and we want to solve for, notice that we're being asked for the linear speed, VF. That means that we also need to remember that V final is going to be equal to R times omega final, just that relationship between the linear and angular quantities.